Okay, so we've been talking about fluids and flow rates and how to calculate such flow rates like velocity or mass flow rate or volumetric flow rate. But what if your fluid is static or it's not moving at all? Okay, so a good equation to apply in that case is what we call Pascal's law. So Pascal's law is expressed as dP dz equals negative rho g over gc. Okay, so P is pressure and Z is the height or elevation. Rho is density. And of course, you have your GGC. And what do they mean? Take note that G is your acceleration due to gravity. Okay. In SI, it's 9.8 meters per second squared. While GC is your conversion between Newton and your kilogram meter per second squared. Okay. So we know from Newton's law that 1 Newton is equivalent to 1 kilogram meter per second squared. So that ratio is known as GC. Such that if we take the ratio of G and GC, it will give us 9.8 Newton per kilogram. So it's the conversion factor between unit of mass and unit of force in SI. Okay, so that means if you have a kilogram of an object, it exerts a weight or a force of 9.8 newtons. Okay, in the English system, the value of your acceleration due to gravity is 32.2 approximately feet per square second. And the GC is 32.2 as well. Okay, such that if you take the ratio G over GC, it becomes 1 pound force per pound mass. So meaning pound in the English system, if you refer to mass or if you refer to force, so they mean the same thing. Okay, so this equation can be applied in columns of fluid such as that of your fluid here inside a tank or a container. So the shape of the container doesn't matter. You could have a cylindrical geometry or triangular or what have you. Okay, the important is the elevation. Okay, now from that equation, which we can actually derive from the Bernoulli's equation, which we will talk about in some other lecture, and also we can derive this using force balance. Okay, and from that equation, you can apply limiting cases and derive these three equations here. So if the case is that your fluid is incompressible, again, incompressible means constant density. The equation in the previous slide will become this. So it becomes delta P equals negative rho G GC delta Z. So let's take a look. The reason is that if you're going to solve this differential equation and rho is constant because it's incompressible, GGC is also constant, all you have to do is integrate dP and dZ and it will become delta P and delta Z. Okay, what if the fluid is compressible? Let's say air in the atmosphere is fairly not incompressible. Okay, so anong gagawin? First, you can assume that air or whatever compressible fluid that you have, you can assume maybe that that fluid, if it's a gas, you can assume that it's an ideal or perfect gas. Secondly, you can assume that maybe the temperature is constant. So you have the case of isothermal condition. So in that case, since you're assuming that the gas is ideal, remember that density can be expressed as PM over RT. Okay? And if you plug that into the previous equation here, density is PM over RT, and do the corresponding integration, you will end up with this second equation here. ln P2 over P1 equals negative GGC M over RT Z2 minus Z1. So again, this is used for compressible fluids at constant temperature, assuming that that fluid is ideal. If the temperature is not constant, okay, you will have to put in the temperature in the integrand, and doing so, you can derive this equation here, all right, where you need a temperature function, okay, which is a function of your elevation. That is true with, let's say, a good example is the atmosphere. So the temperature in the lower layer of the atmosphere is fairly constant, right? Pero sa ibang layer ng atmosphere, medyo nag-iiba yung temperature depende sa altitude. Okay? So we call that lapse rate. Anyway, so the first equation, again, it's for incompressible fluids. You can use that equation, okay, in problems such as how to get the pressure if you have, let's say, a U-tube manometer, given the elevation of the fluid, okay? So you just have to incorporate the delta Z or the delta H. The second equation can be used in, let's say, if you want to get the pressure, let's say at the top of this mountain here, and this is actually a beautiful picture of your Mount Apo in Davao, all right? So use this equation to get the pressure at the top or at any point in that elevation, okay? You will expect that the pressure at the top will be lower compared to the sea level, okay? That's the reason na yung boiling point ng water sa taas ay mas mababa. Tama ba? Kasi mas mababa yung pressure. In other words, the vapor pressure of your fluid, or let's say water, will match the atmospheric pressure here at the top. Mas mabilis yun kasi mas mababa yung pressure sa taas. In a column of fluid, however, let's say, sa baba, mas tumataas yung pressure. Or let's say you have a case of water or in the sea, habang lumulubog ka, mas tumataas yung pressure. So that's practically the relationship. Okay? Again, for the third equation, if the temperature is not constant, however, okay, you need to have a function of temperature as a function of elevation. So in that case, for example, in the troposphere, you have this function. It's practically a linear equation. So just get the slope, and using your maybe point slope form of your straight line, you can arrive at the function and you can put it here and you can integrate. Okay? And so on and so forth. So let's have an example. What are you seeing here is a picture of Titanic's lost sister named Britannic. So si Britannic, ano siya, yung gumawa sa kanya, parehas nung mga engineer and mga gumawa kay Titanic. And its design is such that yung mga naging problema ng mga sister ship niya ay ma-solve or maiwasan, okay, in the design of Britannic. However, this ship sank as well, and the reason why it sank off the coast of Greece nung I think this was during the Second World or the First World War. It's because mayroong minahan ang mga German sa malapit, and yung blast kind of shook off yung ship and nasira siya. Okay? Now, here's my question. Nung dumubog tong Britannic, ay nasa 400 feet below sea surface yung kanyang paglubog. So the question is, what is the pressure of the sea at that depth? Let's assume that the specific gravity of seawater is equal to 1.024. So how do we solve this? First, a few things. Since given yung height or yung paglubog ng Britannic ay 400 feet, so I think the problem is such that kailangan natin i-solve yung problem using English system. So 400 feet siya. So let's get the atmospheric pressure, okay, at some English unit. So again, the atmospheric pressure is 1 atmosphere, but in English system, or in PSI rather, it's 14.7. No? So PSI means pounds per square inch. Okay. Now, remember also that in the English system, approximately the density of water, of course it depends on temperature, no? But the reference or the maximum density of water in the English system is 62.4 pounds per cubic feet. Okay, in the metric system, we know that it's close to 1,000 kilograms per cubic meters, but in the English system, it's 62.4. Okay, so in our calculation, we need the density of seawater. And remember that density can be calculated by multiplying the specific gravity of that fluid by the specific gravity of your reference fluid, which is water. Sorry, specific gravity of the fluid times the density of water. So from the problem, the specific gravity is 1.024. And the density of water is 62.4. It will give you the density of the seawater to be 63.9 pounds per cubic feet. Okay? Now let's apply Pascal's law. Pascal's law is delta P equals negative rho G GC delta Z. Okay? And the reason why we do this or we use this form of Pascal's law, it's because we can assume that the fluid is incompressible. Wala namang given na temperature sa problem, so malamang incompressible siya. Because temperature is the primary factor that affects the density of fluids. Okay, so in expanded form, delta P is P2 minus P1, delta Z is Z2 minus Z1. And we are looking for the density of seawater, which we now have. Okay. Plugging in the equations, it's fairly straightforward. P2 minus P1. So what is P1? Okay, so in this figure here, you can see, all right, that we need to establish first a datum line. Okay, so ito yung reference line mo. Okay, and then that reference line, we can call it, or reference point, we can call it point 1. And then, yung nasa baba, we can call it point 2. Okay. So actually, pwedeng yung datum line mo, yun yung baba, tapos yung taas naman yung point 2. So pwede yun. You can interchange 1 and 2 as long as you're consistent in your solution. So since P2 minus P1, so ang P2, ito yung nasa baba, which is what we're after, right? We want to calculate the pressure at this point. Minus P1, so P1 here is what? Since nasa sea level siya, this should be the atmospheric pressure. Okay? Atmospheric pressure. I'm using my mouse, so I don't have a stylus. Kaya, pardon this. So atmospheric pressure yan. And atmospheric pressure, again, is 14.7 PSI. But what is PSI? PSI is pounds per square inch. Inch pa lang yan. So we have to convert to square feet. So to convert that, we multiply by this conversion factor. 1 feet is 12 inches. Square mo yan. Okay, makaka-cancel yung square inches. Equals density ng C. We now have that. Okay, 63.9. G over GC, remember, in English system, it's 1 pound force per pound mass. Okay? Kapag SI, 9.81 yan. Pero kapag English, 1. And then Z2, where is Z2? Ayun, nasa baba. Okay, kasi kung ito yung datum line mo, which is yung 0.1, okay, all values above that, let's say the elevation, will be positive, and all values below that will be negative. So Z2 is negative 400. while Z1 is 0. Okay? So therefore, P2 na lang ang kulang. And we can solve that P2 is 27,677 pounds per square feet, or in PSI, it's 192. So take note that mas mataas yung pressure sa baba, sa ilalim ng dagat compared sa mas mababa. Okay, next. You have here a beautiful picture of your Mount Fuji in Japan. Okay, it's the tallest mountain in Japan, and this photo is taken in a month of July, where the temperature is fairly low. Okay. Okay. So now, ay sisirain ko muna itong magandang photo na to by putting in some details. Okay, so it's 5 degrees Celsius, ganyan yung temperature. And the height of that mountain is 3,776 meters. Okay? Okay. Now, the question is, ano kaya ang pressure sa pinakatuktok ng Mount Fuji? Right? So, this is the worded version of the problem. Okay, so you have all the details. Now, let's solve this. We cannot assume anymore that the fluid, which is basically air, incompressible siya. So no, it's compressible. Okay? Actually, most gases are compressible. Alright? So, since compressible siya, we can assume na yung air ay ideal. Pangalawa, that the condition is isothermal. And in that case, we can use this equation here. Okay. Now, let's set our datum line. So, let's have yung pinakababa or sea level as 0.1 and yung taas as 0.2. Okay? So, let's apply the equation. Okay. ln P2 over P1. P2 is what we're looking for, right? And P1 is yung atmospheric pressure, which is 1 atmosphere. Okay. I don't have to convert this to any unit because naka-ratio naman siya. Basta yung mga kukuha nating sagot na P2, kung atmosphere yung ginamit sa P1, atmosphere yung lalabas din. Okay, let's substitute the other values. G over GC is 9.81 Newton per kilogram. Okay, SI tayo. Metric system. M is, if you recall, the molecular weight of air is 28.8 gram per mole, right? So in metric units, it's 0.0288 kilogram per kilogram mole. Okay, and then R is 8314 joules per Kelvin kilogram mole. All right? Diba 8.314 siya, pero since kilogram mole dito hindi siya mole lang, i-convert natin 8314 siya. Or you can use 28.8 here but 8.314 here, no problem. I forgot to include times temperature, right? So let me one moment. Times 5 degrees Celsius, right? 5 degrees Celsius in Kelvin, that's 278. Okay, Kelvin. All right. Now let me check if the answer will change. Okay. So temperature is 278. Okay, and then Z2, ayun, ang height daw ng mountain 3776, positive kasi nasa taas, minus Z1, 0. So if you compute that, you will obtain a pressure of 0.9995 atmospheres. Okay. Next, I have here a tank containing oil and water. So oil has a specific gravity of 0.8 and water is 1.0. Let's determine the pressure at the interface. So interface, ito, and at the bottom. Okay. So, ang sabi sa problem, hanapin natin yung pressures dito sa bottom, tsaka pressure sa interface. Now, let's designate our points. If I choose the tawag doon, lead, or yung pinakataas na container as our datum line, so I'll make it 0.1, and the interface becomes 0.2, and yung pinaka-bottom 0.3. Okay? So therefore, ang kailangan natin kunin ay P3 at P2. So P3 at P2. And you're given the specific gravities of oil and water. Okay, so how to solve? Let's apply Pascal's relation. We can assume that wala namang given kasing temperature, so maybe it's incompressible, so we can use this relation. So let's go first dun sa oil. Okay, yung 1 to 2. So that's oil. So applying the equation, magiging P2 minus P1, P2 minus P1 equals negative rho oil, kasi oil lang siya, GGC Z2 minus Z1. Okay. Substituting P2, yun yung pressure at the interface. So ito yung hanapin natin. P1, okay, is what? 101.325 Pascal because it's atmospheric. Kasi nakalagay dito, open siya. Okay. Open siya sa atmosphere. Alright? Now, what is the density of oil? So the density of oil, remember, is the specific gravity times 1,000. SI tayo, kaya 1,000 yung reference fluid natin, which is the density of water. And then GGC is 9.81. Z2 minus Z1, di ba? Z2, 1 meter daw to eh. So that's negative 1 minus 0. Okay, baba siya ng datum line natin, kaya negative. So P2 therefore is 109,173 Pascal. Pascal yan ah. Okay. So that's the pressure at the interface. So take note na mas malaki siya ngayon compared dun sa atmospheric pressure sa taas. So habang bumababa ka kasi, tumataas yung pressure. Now, let's find the pressure at the bottom of the container. So we're going 2 to 3. That's basically water. Therefore, kung 2 to 3 yan, P3 minus P2, Z3 minus Z2. Okay? So P3 is what we're looking for. P2, we know that already. Na-compute na natin yan na 109,173 Pascal. Density of water, it's 1,000. GGC is 9.81. And Z3 minus Z2. Okay? Z3 is what? Negative 3. Kasi 1 plus 2, negative 3. Minus negative 1. So that's double minus ha. So minus negative 1. Kasi minus Z2. Ang Z2 mo negative 1 lang. This is Z2 at nasa point negative 1 siya. Okay? So therefore, P2 is 128,793 pascals. That's the pressure at the bottom of the container. Or we can actually generalize an equation or generalize a formula for that particular tank problem with layers of fluids. So if you want to compute the bottom pressure, you can use this, no? At the atmospheric pressure kapag open siya sa atmosphere, and then it's basically density of fluid A GGC height of fluid A plus density of fluid B GGC height of fluid B plus and so on and so forth, right? In this case, it's just oil and water. If you are going to substitute, you will get the same answer that we computed previously. Okay. We can also invoke Pascal's law in examining this paradox called exploding giraffe's head. Exploding giraffe's heads paradox. Okay? Ang tanong dito is, bakit daw hindi pumuputok ang ulo ng mga giraffe kapag sila ay umiinom ng tubig sa lake or wherever? Okay? Kasi di ba ang giraffe, ang haba-haba ng kanyang neck. Alright? So ang problem kasi dyan, sa napakataas ng ulo niya, so paano yung blood nakaka-flow, napapump from the heart to the head? Okay? Kasi diba, remember, blood should carry oxygen to the head, to the brain. Eh, ang haba ng neck niyan. So paano yon? So it turns out that the heart of the giraffe, which is around mga 2 feet in size, okay, across, ano siya, medyo tough siya. Okay, so it can actually produce lots of or very high systolic and diastolic pressure. Okay, but that's half of the problem pa lang. Okay, the other half is again, kapag iinom si giraffe, paano yon? Kasi kapag if it lowers its head, okay, remember kapag mas mababa yung fluid, sa baba ng fluid, mas mataas ang pressure. So the fluid in this case is blood. Okay? So the blood is too pressurized, nasa baba kasi siya, tapos siya ng ulo. So hindi kaya siya magkukos ng rupture ng brain or ng head ng giraffe. So it might happen, but the good thing is that giraffes evolve so that meron silang special valves along the column ng neck nila that will close, kumbaga it will not allow the passage of blood, okay, or some blood. Okay, so ibig sabihin yung pressure hindi mapupunta sa ulo. So may mga valve system diyan sa neck. And also yung kanilang veins, no, or arteries or blood vessels, they're quite thick enough to withstand high pressure, okay, from the blood. Another problem that you can apply or practice is to calculate the static fluid pressure in the cranium, sa ulo, no, ng tao at the end of both systole and diastole. So if you are going to assume a length from the cranium to the aorta, remember aorta is the largest artery, okay? And then yung pressure, pagka-pump, let's say at the end of systole and diastole is 120 over 80, kunyari yung blood pressure niya. So it's 120 and over 80. Yung mga na-measure yung blood pressure, actually they are measured in terms of millimeters mercury. Okay? So you can apply Pascal's law. So kunin mo lang yung pressure at this point. Okay? You can call it 0.2 and then 0.1 siguro to. And then you can apply Pascal's law. So please practice this problem.